Okay, so the last time, before we all gave thanks, we divided into cases. D is equivalent to 2 or 3 mod 4, and D is equivalent to 1 mod 2. We covered D is equivalent to 2, 3 mod 4 last time. And if you remember what happened in that case is we basically looked at norms and we narrowed it down to the only possibility for an HFD for n bigger than 1 and D negative and equivalent to 2 or 3 mod 4 was we reduced it down to the case when D equals -1 and N was prime. And then we showed in general that even this doesn't work. Right? So now D is equal to 1 mod 4. And the approach, if you missed last proof for the last one, I don't think it's going to make a huge difference because in this case, it's very similar. The approach is. So in this case, let's write R is and again, what I want to do is I want to pick on a certain element and look at its norm. Because consider the norm. Which is the norm of that particular element is n times 1 plus n squared, that is, so 1 minus d over 4. Of course, this is an integer because d is equivalent to 1 times 4. And in general, let me explain something. I mean, it's actually the irreducible element of our segment. All right. So if to establish this, if x plus y if you have a general element in here that divides this, this is not irreducible, then certainly the norms must divide each other. So the norm of the this must divide that. So so that is n squared times 1 minus d over 4 must be divisible. And that is properly divisible, not quotient can't be 1 by the norm And the norm of this is now to make things a little bit easier on myself, I'm gonna rewrite this by completing square. So if I complete the square, let's write in. Not b squared on that. Right, so all this is just completion squared out, right? So in other words, this thing has to be divisible by that. And remember, of course, that d is negative. I'm also going to make the following observation here. We will also assume so if this thing actually divides what I claim is irreducible here, we can assume that this norm of our divisor is no more than no more than that. Anybody explain why? Where did I get in squared? Let's be over 8.
Some factor of, if that's not, I guess, a prime number, then it has to be divisible by something less than or equal to half of it.
Oh, right. That's essentially it. So we're trying to show that this is irreducible. If it's not, it must be properly divisible by some element that looks like this. Well, that means that this norm, the norm of this thing, which is this, must be properly divisible by the norm of this, right? So if this divided by the norm of this, if this is a proper divisor, then its quotient must be, it's got to be at least 2, right? Which means that this thing it can't exceed this, because if you're bigger than this, then this quotient is smaller than 2, right? That's essentially it. And so now we're going to kind of take advantage of that a little bit. So for any fixed value y, the norm that we have over here is minimized. When x minus n over 2y. And this minimum value. So this is just, this is really just calculus here. The minimum value is Okay. So if you're in calculus and you minimize this, this is what you do, and you get this minimum value here. And what this gives us, in turn, is minus d over 4 n squared y squared. Must be less than or equal to n squared times 1 minus d over 8. And so we can rearrange this. Y squared is less than or equal to d minus 1 over 2d, which is less than 1. So we've got this inequality here, in particular, y squared is strictly less than 1, right? And since y simply restrict to integer values, right, this means that y must be 0, or that squared be strictly less than 1. And hence, y is 0, that must mean x divides n times 1 plus radical d. Right, because what we've gone through all this prestidigitation to show is that y is 0, so that means my divisor of this thing right here must actually be an integer. And that's impossible because this is the order of index n. If you divide that by n, that will be a smaller value of n that multiplies that to the ring. So this allows us the conclusion that we wanted. So that was okay, so now, yes.
So maybe I'm missing something. We went through all this process to show that y was 0, but I just have that written down way back, right when we wrote down the form for the norm of x plus y. Because that's already, if y is at least 1, that's already going to be bigger than n squared 1 minus d over 4.
Well, that's right, but I mean, that's what this shows is calculus. I was just being careful. So what you're asserting here, that's what we're.
Before you complete the square, like if you say y is at least 1, then the term on the right is going to be at least n squared 1 minus d over 4, and then you have plus other stuff that's positive. And
yeah, but the x can be negative, right? And so, I mean, is it so clear, really?
Good.
Right. So once we've gotten whatever road you take, once we've gotten this is irreducible, let's look at the following factorizations. So consider factorization. And it's so it's gonna be kind of cool here. By the way, I proved that this was irreducible and not this one. However, this is the automorphic image of this one, so it has to be irreducible as well. So this is n squared which is n times n. Oops, 1 minus. Now, I've got two factors on this side. And it looks like I've got, too many on the other. Or do I? So everybody okay with this? The fact that these two are irreducible, I've nailed this down. There are two irreducible factors on the side. So this is fine. This has got at least two, right? Over here, notice that n is bigger than one. So this counts for at least two, right? What about this? This is extra, and you've got too many factors unless one minus d of 4 plus minus 1, right? Because 1 minus d over 4 is an integer, because d is equivalent to 1 minus 4. And so the only way that you don't induce extra factors out of that term is if that is plus or minus 1. Whoops, yeah. Yeah, that's right. And what does this mean? This means 1 minus d is plus or minus 4, or d is plus or minus 4, plus or minus. Well, it certainly ain't 5, so d is negative, right? So to avoid contradiction, we must have d is -3, right? Gotta have that. And what else do we have to have? N must be prime. Because if n is not a prime integer, then you've certainly got more than, you've got a whole collection of factors there. Correct? Now let me point out, we know d equals -3, n equals 2 does give the HFD. Because we proved right before the break, see it joined negative. The joint square root -3 is an HFD. So our aim at this point is to show, so we've got everything down except for the odd prime index in z adjoined with omega, where omega is 1 plus radical -3/2. So all we gotta do is throw out the odd primes. And the way we do that is similar to the way we handle the Gaussian integers. Right. For the last little bit, so it remains to show if P is an odd prime and omega is that way, I'll do the cube root of unity here. Right. Actually, maybe I'll do it keeping with I'll do the 6th root of unity. Then z adjoined with p omega is not an HFD. So if we eliminate this last case, then we're done. Everybody agree with that? So to this end, let's see what we do here. Let's look at the norm. let's see what this is. This is gonna be P squared plus P times omega plus omega bar. So this isn't the third root, so I might have to change things a little bit. Squared. And this is P squared times omega bar. Which is P squared, omega plus omega bar is 1. Right, when I add that to its complex conjugate 1. And when I multiply it by its complex conjugate, I get 1. So the norm I get is 3p squared. Okay. So I'm going to claim that this is irreducible. Right. Okay, so the norm is 3p squared. So if not, there is a proper divisor of P plus P omega of norm 3 or by the way, Y3 or P.
Even not know about you, that's P.
Right, right. So let me make sure that we're all on the same ship here. If that's the way it breaks down. I don't think I missed anything, right? But notice there's a certain amount of symmetry, right? Got one of these, got one of these, and one of these. Notice that this factorization doesn't count because that means one of them has to be a unit, right? So notice that the only interesting factorizations left over, you must have an element of norm P or 3, right? So let's try to eliminate that. If A plus B P omega the norm is B let's see, that would be let's see, so that'd be 1. Right. Now I'm going to rewrite this here. This might be useful to us. Now, the first thing I want to point out here is that it's impossible for there to be an element of norm P. Can someone explain it to me?
P would have to divide A.
Well, of course, let me also point out that you don't have to worry about negative P, do you? Because this norm is always positive, right? If the norm is P, right? If this thing comes to P, notice this and this are divisible by P. This implies that A is divisible by P. Right? And if A is divisible by P, then that means that the norm of A plus B P omega, well, this is the norm of A prime P plus B P omega, because after all, A has a factor P in it. And this is going to be P prime P squared A prime squared plus A prime B P squared plus B squared P squared, which is divisible by and that's a contradiction because P is not divisible by P squared. So, okay, that's out. So that's not possible. So the only thing that we could end up being stuck with is to have this decomposed into something of norm 3 and something of norm P. And there's a couple of ways to do this, but you could argue that you can argue what the elements of norm P squared would be like. But here's another way to do this. If let's just suppose for the sake of argument, that's true. I do have a pea-sized little brain, don't like fractions too much. So I'm gonna multiply both sides of this by 4. So I get 2A plus BP squared plus 3P squared P squared is equal to 12. Multiply that out by 4. Notice that B cannot be 0, right? Because if B is 0, then that means 12 is a square, which is impossible, right? And so if B is not 0, what's that? Therefore, so P is less than or equal to. And that's a contradiction because we assumed it was not. And so finally, the death knell of this is so this is the odd prime case, irreducible, irreducible. And it leaves 3 factors on the other side. And that wraps it up. We eliminated the case for D equals. In fact, it's interesting how the proof works, because in the first case, when D was equivalent to 2 or 3 mod 4, we reduced down to the case of the Gaussian integers, and the n had to be prime. Okay, and we tossed that completely. And then in the other case, we reduced down to n equals 2, and p must be a prime. We know the even prime work, and the other primes now too. Okay, any questions on that?
So this is for the HFD case. Is there similar restrictions for rings with elasticity 3 halves?
I mean, yeah, all that stuff will be encoded. And we'll talk about what elasticity is, but actually, it's funny you say that, because I'm going to use that as a segue into the next. Any questions for it? Okay, so it's going to look, as I'm sure it often has in this course, like I'm having a stroke, because I'm going to do this example and play around with prime ideals a little bit, and then I'm going to start talking about Euclidean groups. And what is the connection, you may say? I promise you there is one. So I want to go back to this ring here. Now, if you recall, so the inspiration was my first desire to give an evil factorization. And in this ring, these are 2 factors of 81 that we've already argued are irreducible factorizations, 1.4, 1.2. You remember what this one was? Yeah, it was C mod 4Z. And in fact, in this ring, one of the things that is there was a principal class. Corresponding to 0 bar. So one of the some of the machinations we went through earlier is I gave examples of prime ideals in every class. Oh, by the way, let me note this down from home application. We went through some to show that the order of this is exactly 4. The order of this is 2. The order of this is 4 as well. We showed these 2 classes are inverses of each other. And then we showed, okay, look, the class group contains a subgroup isomorph, Z4. And then we threw the Minkowski bound in it and said, okay, it's exactly Z. All right. By the way, just for giggles, can somebody, one of these things is not prime. Prime ideal, prime ideal, prime ideal. The ideal generated by 1 is in the principal class for sure, but it's technically not a prime ideal. Anybody give me a prime ideal in that class? Let's see if you can.
17.
Yeah, okay, so how do you know?
Because the norm, you can't, it cannot be able to.
Right, but how do you know it didn't split into 2 non-principal primes? So the easiest way I would say is how about this? Let's go.
Oh, come on.
You beat me to it by 1 second, because it has a prime norm.
It's got prime norm. See, that's how I know it really quickly. Because the norm of that is 9 plus 14, which is 23, it's a prime norm. So the element has to be prime. So that's a quick way to do it. There will be primes in the principal class that do not split. And Adam very likely might be right, but it's harder to check, I think. I mean, you can certainly do it, but you would have to check and make sure that you want minus 14 to not be a square minus 17 and so forth. So you'd have to do the Legendre symbol, and we'd make Rodrigo go to the board for that, so he can get all angry at me.
I got it now.
After, I thought you had like a deep intense hatred for that.
Well, no, yeah, it's my master.
Oh, just friendlies.
Yeah.
So, anyway, so there's a prime in the principal class, right? So I want to look at some principal ideals here that one might build out of sheer lack of social life. So how about this? Let's look at right. So in my notation, for this example, PI QJ are primes. So whenever I use subscripted P's and Q's, and do I use another one? And NK are primes. And XI means prime ideal coming from class corresponding to I bar and so what I mean is a prime that comes out of this class might be P1, a prime that comes out of this might be Q2, Q3 out of this. And I would subscript it 0 for the principal, but I'm not gonna mess with that because that didn't really add to the proceedings here. So first of all, let's look at this. Okay, so let's pick, and by the way, this is another cool thing about this example. These are rings of algebraic integers. Not only do you have a prime in every class, you got as many as you want, right? Infinitely many if I so desire. So let's pick a prime out of this class and take it to the 8th power, right? Would everybody agree that since the order of P1 in the class group is 4, this is certainly a principal ideal, right? Here is my question about this. Well, let me go deeper than that. What are the element principal ideal? These are almost, except units are ignored. Factorizations. Next one. Right. X1 as an ideal is P1, 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 1, P1, 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 P1. Now, how are you going to get irreducibles out of it? These are all the same prime ideal, and you only get them in clumps of 4. And there's only one way to do it. Let's call this alpha. And let's call this, well, alpha. Up to units. X1 is alpha squared. It factors uniquely. Now that should probably grab your interest a little bit, because the element X1 factors is the product of two irreducibles. In fact, it's the square of an irreducible, alpha. And that's the only way to do it. This ring itself is not a UFD. However, this particular element factors uniquely. It's not irreducible, but there's only one way to factor. That's it. All right. Okay. How about this one? What if I did this? So I should say. What about this one right here? Oh. How many factorizations does this one have? Or how can we factor this one?
Your P1s all bunched together.
Alpha, beta squared, or some gamma squared. Six
So
squared.
we have now notice this one comes out of, so and this ideal class P2. Sorry. How many ways can we do this? Remember, the P2 comes out of the ideal class board 2, correct?
So you either keep your P1s all bunched together.
Okay, so yeah, so I'm gonna use parentheses to denote different. So Grant's suggesting this. And then what else?
2 copies of P2s.
Is that it? There's a lot of other things. What else can we do?
P1 squared, P2. All of that squared. P1 squared times 1 P2.
Comes 1 P2.
That all of that squared
Okay.
times P2 squared. On its own.
Anything else? Well, I guess maybe the key is you might ask yourself this, self, how can I build irreducibles? Right? The irreducibles that I can build. Right? So you can go off broke this way, right? This is class group is 4, right? So notice if you have P1 cube, you have to have the other P1. You're no chance otherwise. So if you have 3 or 4 of these, you have to go all the way to P1 4. If you've only got two of these, you can do that. And that's kind of it, because if you only have one P1, you've got to put at least two P1s in there. Because if you have a P1 and a P2, then that gets you up to like the third, the 3-bar thing. And so to be reduced, you just got to show me more. And there's one more way. And that's just P2 squared, right? And so now you start eliminating. Like you think, what happens if you have P1 to the 4, right? Well, if you have P1 to the 4, the only other way to make this irreducible factorization is to do this, right? So that's it with P1 to the 4. And if you have one of these things, then after you eliminate this, P1 squared P2. Well, now, because these are class number 2 and these are class number 4, you need 2 of these and another one of the other ones. So it looks to me like those are the only ways to do it, doesn't it? But ask yourself some other things. So let me give you suppose these are all these class here. Do that, right? If they're all from just the same, they're all from the same ideal class 4. Right? And what happens if the first 4 are from the 1-bar class and the other are from the inverse class? Right? So anyway, we'll talk more about that next time. Any questions? All right, like I said, next time we'll pull more of this kind of factorization, and then I'll show you how this leads us in a natural way into a little bit of finite abelian group theory. All right, y'all have a good one, and we'll see you on Wednesday. Oh, great. Yes. I hope it's a good time to get back.
I guess today, probably, like, if you want to come today or.
Oh, yes, sure.
Sure. Probably like 2 or so.
Okay.
Yeah, so that'll be fun.
Okay.
Yeah, thank you. Oh, so kind of remember.